Welcome, geologist. We're going to be learning about the geologic timescale. This is such an important part to our course, and there's a few things I need to preface about the geologic timescale. Number one, it will change. Number two, the dates are not consistent between different scales that you might look at on the internet or even in textbooks. There's a reason for that. We'll talk about that during this lecture series. Most importantly, the geologic timescale is a combined relative and absolute dating scale. Didn't start off that way, but it has certainly ended up that way. So as we start our journey from even below what this timescale shows, and this is just an artist's depiction, with I kind of like it, it's fun, showing you the beginning of where we have a rock record. If there's actually a period of time prior to that, that is the earliest segment of the Earth's history that some geologists don't even recognize, since we don't have a rock record for it. But we do know, not just on faith, but on evidence in the rock record, that this time actually occurred. So each one of these divisions represents something important, and I kind of like the way this artist has depicted this important set of life forms that evolves throughout the segments of geologic time. I might also add there is a structure, a rhyme in terms of patterns of how this time scale is put together, and also a color schematic on what you would find on any map that's a geology map that uses universal colors in order to denote specific time frames. So the geologic time scale has a history, and it's one that we're going to look at today and then explain how we came up with the current version of it and then how it could change in the future. So why do we even need to study geologic time? Well, I'm going to start by looking at these remarkable stromatolites in Shark Bay, Australia. I made a trip all the way to the western, as far west as you can go, Australia, just to see these things. It was on my bucket list to do in life. I'd already seen the other most famous colony of these in the world that are living today, and they're in the Bahamas. And I wanted to find out what made these so different. And then, having seen fossilized stromatolites in the field in many places all over the world that I have visited, I wanted to understand the living counterparts of those. These are living fossils. What that means is they have been alive for such a long stretch of geologic time. I don't mean these specific stromatolites, I mean stromatolites in general. And they've left a record for us all the way back from the Precambrian to modern day, appearing in the rock record regularly in the same types of depositional environments. So we look at the geologic time scale and we study geologic time in order to understand and turn the pages back to the beginning of the Earth's inception and try to piece together a story based on clues that we find out in the field to help us determine what really created this magnificent place that we call home. So we use fundamental strategies and principles to help us solve these problems, much like you would use certain mathematical equation systems to solve a math problem. We use the same problems solving skills in geology with just a different set of tools. So let's get busy starting and learning about that. You must understand that there are two distinctive types of geologic time. If you've done your textbook reading, and you need to be keeping up with your textbook reading, then you have read this chapter before you watch this video. And I strongly urge this semester that you take the time to read before you watch these. It'll help you when you are watching these videos to have some prior knowledge, and then the videos will kind of home in on the key points. Relative dating is different than absolute dating. The time scale was originally developed to be relative dating. Here's what I mean by that. If I throw out a couple of examples of things you would relate to from specific time frames, I think you would relate to how relative dating operates. And I'm just going to say Pearl Harbor. That rings to a time frame, doesn't it? You think back to George Washington. Does that bring back an era of time for you? If I think about a muscle car like a GTO, it was one of my mom's favorite cars. We still have it in our family, a 66 GTO. That's a legendary muscle car from Pontiac. What if I say something like Elvis Presley? Or I say something like ZZ Top? These are things that you would know through history of even just being alive at your point in your life that you would recognize as important, people that had significance. If I said something like Richard Nixon, a whole history would come into context there. If I say Roosevelt, a whole nother context comes into play. Well, that's what this relative timescale is supposed to do for geology. It gives us a relative age of the sediments, and I might add the fossils that are in those sediments. The question is, how can we get more specific and more detailed about how the accuracy of these data points are on the geologic time scale? That's where absolute dating comes into play, but you have to understand that absolute dating really didn't come about till around 100 years ago, give or take a little time. And why is that significant? It's significant because absolute dating is corresponded to radiometric dating and isotopic dating. So isotopic dating is the most common method of dating rocks. So the first thing that people would say is, okay, well, you've got this right here. This is Mammoth W from the Mammoth site in Waco, Texas. She's a really beautiful specimen. I'll just give you a little bit of knowledge you may not know, but I'll just tell you anyway. Her teeth right in here are whoever prepped this cleaned them a little bit too well, because the stuff they needed to do some testing about what she ate last isn't there. So she had a pretty good dental job done to her. She's young. So she's less than 70,000 years in age. Why is that important? Because we can use the most famous type of radiometric dating, which is carbon-14 dating. You can't use carbon-14 dating on really old rocks, and we'll get to why shortly. So how did the evolution of the timescale really become a reality? Well, William Strata Smith had some helpers that helped him develop those first series of geologic maps back in and around 1815-ish. And what happened was, once those maps were published and available for people to utilize, the value clearly became transparent as to how this could be used for economic gain. So new studies started happening on localized and regional outcrops of geology in order to make more maps similar to what they had done. So what had happened was people started naming rock layers and naming them from a local perspective, usually related to the area in which they were first being mapped and analyzed. So naming rock layers became a standard practice, as still today when rock layers are mapped for the first time. Ultimately, large-scale studies indicated that formations weren't just localized, that they were regional, and even beyond regional on a larger scale, which meant that we needed to look more comprehensively at the rock record and map outcrops further away from the origin source of which we initially started. And I'm going to use this one as an example. This is the Navajo sandstone found in Zion National Park, but the trick is that Navajo is not just in Zion. It exists all throughout the Southwest and the Colorado Plateau. It is a regional formation. So if you just took an isolated point like Zion National Park and assumed that only Navajo is there, you would soon find, if you traveled any distance away from Zion, it extends for hundreds of miles away from that location. which puts a whole new twist on understanding the geologic conditions that existed in the early Jurassic when this rock layer was made. That indicates that the desert conditions that made this incredible sandstone unit, cross-bedded sandstones, is substantially large Aeolian desert-like conditions, not just a small isolated region. What else was the reason for the need of a time scale? Fossils were being collected in these rock layers that people were mapping, and they were showing similar assemblages, which you will learn more about in the fossil lesson. Assemblages are basically groups of fossils, and they existed, these assemblages, in different localities, meaning that they were widespread, which led to some questions as how could that be? Why do we have the same kind of fossils occurring in multiple different places in Europe? So the geologic map of all Western Europe came to be as a consequence of this really fast tracking, trying to get the area mapped after William and Culver's first map was issued to the public. As more and more mapping occurred, divisions became a reality, and meaning divisions to the time scale. And everybody that mapped these localities began to start to put names to them. For example, this is a fossil from Tucumcari, New Mexico, at the dig we do on our field course, from this outcrop right in here. This is the tooth of a very unfriendly vertebrate that was a carnivorous crocodile-looking animal called a phytosaur. So this particular formation name is called the Redonda Formation. Fun name, isn't it? But the Redonda Formation is a late Triassic, actually the latest of Triassic, and then phytosaurs go abruptly extinct. So we can see that in rock layers well outside of eastern New Mexico. Phytosaurs are found right near Lubbock, Texas, around other places around the world. But if you look at this, you can correlate that the same types of sediments, same type of aged rock layers, these phytosaurs are found. So some famous names got assigned in the development of these maps of Europe that first occurred. Cambria represented the oldest rocks of Cambrian age that were observed and mapped in Wales. Well, Wales is right near England and Scotland. I've been there and can tell you that it is a coastal island, basically. The entire British Isles are. And this particular term came from ancient Roman name for the country Wales. So Cambrian's probably one of the more famous rock layer names simply because it's the basal unit of the Phanerozoic. Another famous name would be Silurian, named after Silures. Silures was younger rocks that were on top of these Cambrian aged rocks in Wales, and they're named after a Welsh tribe called Silures. So there's still a rock layer in between these that we'll address later on called the Ordovician. So it goes Cambrian, Ordovician, Silurian. Well, Carboniferous is a unique term that was applied to coal-bearing rocks from the late Paleozoic in Britain. Well, we correspond that Carboniferous with Mississippian and Pennsylvanian here. There'll be a larger discussion on why we separate those two out and Europe does not. Devonshire is a place that's named after a locality in Wales where rocks were first studied of a very interesting set of intermediate rocks. Well, if you think back to what you learned in geologic time, intermediate rocks was one of those first proposed types of rocks from the flood that we learned about in the first lecture series. And so Devonshire contained both Cambrian and Carboniferous rocks, and there were rocks that were intermediate between them, meaning rocks that were of age somewhere in between those two deals, or those two time slots. Those are now called Devonian for Devonshire. So some more rock layers that ended up being the Mesozoic era came to be. While these are not in sequential order as they are in the geologic timescale and the rock record, these were how they were named in order. Juras is a term that applies to a group of mountains that was mapped out near Italy. And these Jura Mountains showed to overlie some older rocks that are named Trias. They're named Trias, which is a locality in Germany. So Triassic period for Trias, these particular rocks are the basal units, which is what this layer is right here. This is the Chenley Formation, which is late Triassic. Also the same rock layers that are age time frames that contain those phytosaur fossils that we were talking about. So above the Jurassic, we have a chalky limestone layer, and the word Creta means chalk. So that's what the Cretaceous period ended up being named. So the Mesozoic is named after a series of various different localities and then a specific rock type in the case of Cretaceous. So some other famous names were assigned that are younger rocks. So the Quaternary and the Tertiary, and there's quite a bit of controversy over Tertiary. Quaternary is the name that was applied to erratic boulders from glaciers that were found throughout Europe, and subsequently, we certainly know in North America. They were initially thought to be deposited by the Great Flood. Now we know that they were very young deposits that were made in the last ice age. We now know that these sediments are very young from the last ice age, and there was a gentleman that we will learn about in the very last lecture series that proved the theory of glacial erratics. Tertiary is a much more controversial name. The International Commission on Stratigraphy has formally dismantled the Tertiary and renamed it Paleogene and Neogene. Many time periods scales still keep them in the lineup of meaning Tertiary and subdivides the Paleogene and Neogene into subperiods. So the name Tertiary was applied by Lyell that you learned in Geologic Time to younger sediments that he described as Tertiary. So we now know that there's a lot more complex information in Tertiary aged rock, and even though Tertiary represents the earlier section of the Cenozoic, well actually a majority of the Cenozoic, it has a lot of controversy should it be changed. And we'll get to why, but the obvious reason, once we investigate that in test number 3 material, is really about the Cretaceous-Tertiary boundary, known as the KT boundary. And that's the boundary where non-avian dinosaurs went extinct among many things in the ocean and marine vertebrates that were reptiles and a number of other species, even including microscopic foraminifera. So more to come on Tertiary. When the divisions occurred, a couple of guys got credit for naming some of them. Sedgwick and Murchison named some of the most famous: Cambrian, Silurian, and Devonian. And they understood that there was a need for stratigraphic classification of rock layers based on a general relative age, and understood that likely a time scale needed to be developed that could be universal, and fossils would play a huge role in that process. So the universal time scale exists in any language. It's based on specific designations. It goes from really large to tiny in size of age. The European standards that were initially applied to making the initial time scale are so deeply rooted in the culture of the time scale that it's remained as the system that was put into play several hundred years ago. So rock divisions are named universally because they can be found continent-wide and sometimes worldwide. So the timescale designations begin with the largest designation known as an eon. What's the magic term for an eon? That's kind of a controversial question as well. Typically anything that could be greater than 542 million years in age. And why do I throw that magic number out? That's the length of time for the Phanerozoic currently. So Eons are vast amounts of millions, hundreds of millions of years, usually 500 million years or more. So eras are the next dividing point in the geologic time scale, and they represent chapters, for a better lack of words. So let's compare the divisions of the time scale to a book. I'm going to start with eons being something like Lord of the Rings. There are many books that make up the Lord of the Rings, many stories, right? And the story books, each book would be an eon. Each chapter would be an era. So within a chapter, lots of specific things happen. Storyboarding's going on. That storyboarding is going to be a period, so a chunk of time that's unique to that particular storyboard. If you get to a very short glimpse of an immediate action scene, that would be an epic. And if you're looking at one solitary time frame, that would be an age. So most of the time in this course, we would make it down to the epic, not the age. The age tend to have very long, difficult names to pronounce, and they're usually directly correlated to the people who discovered them. So there are only two eons. There is the Precambrian and then the Phanerozoic. Should be obvious that Precambrian represents anything earlier than Cambrian in age. Cambrian is the basal formation of the Phanerozoic eon. So there is a dividing point, and we'll talk about why shortly. So what were the challenges for absolute dating? Geologists knew for hundreds of years that time would be manifested in certain rock layers. For example, this Jurassic rock layer right here, which is Checkerboard Mesa from Zion National Park. And they knew that some layers were older than others, but they had no idea exactly what that perfection rock layer was in terms of age. They didn't know when it started, they didn't know when it finished. They could just judge it based on contact formations of what they mapped in the field and fossils. So the discovery of radioactive materials, isotopes, gave geologists the tools they needed to start putting a reliable start and finish clock to when a period began and when it ends. Subsequently, that would evolve the time scale to not just be relative, but start to have absolute dating points. So what is absolute dating? Essentially, it is a clock that is put into rock material. It goes back to just a basic understanding of how elements are made. All atoms have a nucleus composed of a proton or protons and neutrons, and what will end up happening is the number of protons in that atom defines specifically the element's atomic number. So there's an atomic number element chart. Most all of you have seen that, and it delineates the elements that we have on Earth, right? Not all elements have the same number of neutrons in their nuclei, and these are called isotopes. So this is kind of the interesting part. Some of these isotopes are special. They actually are unstable and decay into more stable versions of themselves. So geologists can measure the decay time frame that it takes for the unstable isotopes to become more stable, and then use that as a ratio tool to determine an actual age. Ultimately, that's referred to as a half-life. So there are two types of decay processes that happen, alpha and beta. And some elements experience just one decay step when this occurs, and others do multiple versions to reach the same unstable to stable condition. The half-life is very important in understanding isotopic dating, because the half-life of a radioactive element is specifically the amount of time it takes for the original unstable parent element to decay its atoms to the stable daughter element. So however long that takes, and that's referred to as a half-life. So the half-life of any given radioactive element is constant, meaning it's a very reliable clock, so it gives us precise measurements. If we can find those isotopes in rocks, we can date them. So this would be an example of a cluster appearance. The half-life would be where we'd lose half of those, and the green's going to represent your daughter. So you go through a second half-life time, you can see you just have a handful of parents left. This is important to understand because eventually you're going to run out of the red dots, right? So you're going to have very little traces of anything to measure a data. That means we have to choose the appropriate clock in order to date the rock. So this is a super place to take a break. We'll come back in just a little bit and learn more about absolute dating and how it helped us achieve a much more precise geologic timescale. So see you back soon, and come back to learn more about geologic time. Bye.